Okay, so this video is going to be on the derivative rules because I figured if we're going to move on with calculus, a better model of this lecture series like an actual calculus class, and usually in those you would have to memorize the derivative rules for different types of functions. And so I'm also going to introduce the new notation that's required for calculus. Instead of using like delta y, delta x for the slope, that is going to now be dy dx, because the delta, the change in each of those variables, is now infinitesimally small. We're assuming it approaches zero, the change. So we write it as d. And that's called Leibniz notation. But Newton, when he invented calculus, his version, he wrote the function f prime of x, and that's the derivative. And so you'll see here that the function is y. Same here, but I factored out the d over dx. And that's usually how you write the derivative of a function. Like if you want to take the derivative of x squared, you'd say d dx of x squared. And then you evaluate that, and we will in a second. But yeah, so the first derivative rule is the constant function rule. And that states that the derivative of any constant function is 0. So the derivative of 1 is 0. The derivative of 100 is 0. And that's because a constant function, a function like y equals 1 or y equals 100, is just a line at whatever. So y equals 1, if that's the function, it's just a horizontal line, and it has no slope. And the derivative is the slope. So the derivative of any constant function is 0. And now, the next rule, the power rule, the derivative of any x to a constant power is n times x raised to the n minus 1. So whatever n was originally, we're going to multiply the whole function by that, and then the n in the exponent, we're going to subtract 1 from it. And like we did in using the definition of the derivative video, we found the derivative of x squared, we saw it was 2x, right? So we multiplied the whole thing by 2, and then we had x squared, and we took the 2 in the exponent minus 1, so we got 2x. So the derivative of x squared is just going to be 2x. And that goes for any polynomial. You can check that with the definition of the derivative, but x raised to any power, it's going to be that power times x to that power minus 1. Okay. And now the variable exponent rule, let's say you have a constant raised to a variable. That's an exponential function, but not the exponential function, but it is an exponential. Its derivative is going to be equal to the natural log of a times a to the x. And the same goes for this one. E is just a really special number. It's an irrational number. It's actually a transcendental number. But it's a very special number because its derivative is itself. And that's because the E function is the inverse of the natural log function. So if we evaluated this like this, and we had the natural log of the base, which would be e, natural log of e is 1. So we'd have 1 times e to the x. So the derivative of e to the x is e to the x. And probably one of the most important derivative rules is the product rule. And that applies when you're trying to take the derivative of a function times another function. So you have a function times a function, you want to take its derivative. How do you do that? You use the product rule. And that states that the derivative of those two functions multiplied together is the derivative of the first function times the second function plus the first function times the derivative of the second function. And the quotient rule is the rule that you use when you're trying to take the derivative of a function divided by another function, in this case f of x divided by g of x. And it's kind of similar, but a little bit different. So the derivative of a function divided by another function is f prime of x, or the derivative of the first times the second minus the first function times the derivative of the second divided by the second function squared. And we'll do the chain rule, which is arguably the most important rule, in the next video. We'll have a whole video for that.